Action potentials propagate in a continuous fashion in unmyelinated axons. Once an action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So, action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way. Summary: propagation of an action potential. Once generated, the action potential propagates the entire length of the axon without decrement.